Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at linear operators and the vector space of linear operators. So in this topic we will review the properties of linear maps with composition, discuss linear operators with composition, describe the identity operator, define matrix powering, discuss consequences of non-commutativity of matrix composition, describe matrix polynomials, and define inverses. Now recall that the collection of all linear operators mapping a vector space U onto itself is represented by script L of U. It has scalar multiplication, operator addition, and operator composition, and thus it has the following properties. The collection forms a vector space under scalar multiplication and operator addition. The additional axioms are associated with operator composition, including the fact that composition is associative. Composition distributes over operator addition from the left, and it distributes over operator addition from the right. We need two separate rules because we will see that operator composition is not commutative. Composition is also bilinear. However, all of those were for general linear maps. For operators, we have one additional axiom. There exists an identity operator such that A composed with the identity operator is equal to A, which is equal to the identity operator composed with A for all linear operators A. Theorem: the linear operator I identified as I applied to U is equal to U serves as the identity operator. Proof: well, A composed with the identity, this identity operator applied to U is by definition A applied to the identity operator applied to U. But the identity operator applied to U is just U, and so therefore A times I, or A composed with the identity operator, is equal to A. However, on top of that, we can multiply that on the left by the identity operator, and consequently, we get that I times A, or I composed with A, is also equal to A. So therefore, yes, the identity operator that maps all vectors in the vector space U onto itself serves as the identity operator. Note also that this means that I does commute with all linear operators A. Now, a vector space together with a composition and an identity operator that satisfies the 5 additional axioms we saw is generally defined in mathematics as a unital associative algebra. Yes, that's a mouthful and you don't need to know that for the exam. Thus, the focus of this course will actually be looking at unital associative algebras of linear operators mapping vector spaces to itself. Hence the name of the course, Linear Algebra. However, we're going to keep things simple. We will continue to refer to script L of U as the vector space of linear operators mapping a vector space to itself, and it is assumed that it has a composition of operators as well as an identity operator. So for script L of R of n, that is, all linear operators that map Rn onto itself, These operators can be represented by n matrices, and the identity operator is the n by n diagonal matrix. Now, recall from fields, the multiplicative inverse of 1 is 1. Well, notice that I composed with I, or I times I, is equal to I by definition. Hence, we have found the compositional inverse of I, and it is itself. Now, rather than calling it the compositional inverse, we're just going to call it the multiplicative inverse. And we're going to be more and more calling composition of linear maps and linear operators as multiplication of linear maps and linear operators. Now, for any other linear operator in the vector space of all linear operators mapping U onto itself, if there is a second operator B in that same space such that A times B is equal to B times A is equal to the identity operator, then we will say that A is invertible, and we will denote its multiplicative inverse as A with a superscript -1. Now, there are two additional field axioms that do not have analogous axioms for linear operators. First of all, operator composition is not commutative, or operator multiplication is not commutative. Not all linear operators have compositional or multiplicative inverses. For example, we note that 2 by 2 matrices represent all linear operators that map R2 to itself. Consequently, we can determine the composition or multiplication of two such matrices. Here we have two such matrices, and when we multiply them, we get the matrix on the right, 0, -1, 2, 3. If we multiply these two matrices in the other order, we get a completely different matrix. So this is just one example that matrix-matrix multiplication is not commutative. Also note that if I have this matrix here, 0, 0, 0, 1, and I multiply it by an arbitrary matrix A, B, C, D, the matrix that results is 0, 0, C, D. Consequently, there are no possible values of A, B, C, and D such that the result is equal to the identity operator, because the first entry on the diagonal is guaranteed to be 0. Consequently, we have found a non-zero 2 by 2 matrix that is guaranteed to be not invertible. So this can never, under any circumstances, equal the diagonal matrix. However, if I have the matrix 1, 2, 3, 4, and I multiply it by the next matrix that is to its right, then if we multiply that out, we do get the identity matrix. If we multiply that matrix on the right by the matrix 1, 2, 3, 4 now on the right, then we also get the identity operator. Consequently, the matrix 1, 2, 3, 4 is invertible, and its inverse is -2, 1, 1.5, -0.5. You'll also remember in fields, if y is the multiplicative inverse of x, then x is a multiplicative inverse of y. And here we can see that holds as well. So the multiplicative inverse of 1, 2, 3, 4 is the matrix next to it. However, the multiplicative inverse of the matrix next to it is the matrix 1, 2, 3, 4. Now, we can also define powers of operators. So if A is a linear operator on a vector space U and we have a non-negative integer n, we can define A to the 0 as being the identity operator, and we will define A to the n as A multiplied by A to the n minus 1. So this gives us a definition that essentially says A to the 4 is A times A times A times A. As a bonus, for an invertible A in the vector space of all linear operators on U, for an arbitrary value of n, we will define A to the n as the multiplicative inverse of A raised to the power negative n if n is less than 0, the identity matrix or operator if n is equal to 0, and the above definition if n is greater than 0. Now, it's always nice to have some familiar theorems from secondary school. So the following is true. If A is a linear operator mapping U onto U and m and n are non-negative integers, then A raised to the power m plus n is equal to A to the m times A to the n. As a bonus, if A is also invertible, then we can allow m and n to be arbitrary integers, and this is still true. Also, if m and n are non-negative integers, then A to the m raised to the power n is equal to A raised to the power m times n. And once again, if A is invertible, we do not have to restrict m and n to be simply non-negative integers. In this case, m and n can be arbitrary integers, including negative integers. On the other hand, not all common simplifications from secondary school work. In secondary school, you saw that xy all squared is equal to x squared times y squared. However, for linear operators, multiplication is not commutative. So ab all squared is not equal to a squared b squared. Instead, ab all squared is equal to ab. Only if you have two matrices A and B that do commute do you get the result on the left. Also, a plus b all squared is not equal to a squared plus 2ab plus b squared. The correct answer is that a plus b all squared is a squared plus ab plus ba plus b squared. Again, you got that from FOIL. However, in secondary school, you got x times y plus y times x, which simplified to 2xy. Now, this, however, still works. Alpha times a raised to the power n is equal to alpha to the n times a raised to the power n. This is also something that should be familiar, and this is a consequence of I being the identity operator. Now, if this does not look familiar, I'd ask you to consider this polynomial expansion of x plus 1 raised to the power n. As you can see, all of the multipliers are the same. The only difference is that we have replaced the variable x with an operator a, and we have replaced the trailing 1 with the identity operator. Now, if A is a matrix, the inefficient way to calculate a to the n is to start with A and then multiply that by a total of n minus 1 times. Here's a much more efficient definition. A to the 0 is the identity operator. A to the 1 is A. If A is raised to the power of an even integer, then A is raised to the power 2 times k for some integer k, then we will calculate a to the k and square that. If A is raised to an integer that is odd, then that integer it is being raised to is of the form 2k plus 1. In this case, we will calculate a to the k, square that, and multiply that by 1. Thus, if n is even, it requires 1 matrix multiplication. If n is odd, it requires 2 matrix multiplications. So, for example, suppose we had a square matrix and we wanted to calculate a to the power 49. Well, to do this, let us use this formula. So to get to a to the 49, 49 is odd, it's twice 24 plus 1. So what we need to do is we need to calculate a to the 24, square the result, and then multiply by a. But wait a second, what do we need to get a to the 24? To calculate a to the 24, we must calculate a to the 12, and whatever that evaluates to, if we square it, we will get a to the 24. Okay, how do we get a to the 12? Well, we must calculate a to the 6 and square it. And how do we get a to the 6? Well, to get a to the 6, we calculate a to the 3 and square that result. And how do we get a to the 3? Well, to get a to the 3, we retrieve a, square it, and multiply by a. That's following the formula exactly. So notice that every squaring is a matrix multiplication, and we have to square something a total of 1, 2, 3, 4, 5 times. Additionally, we must also multiply an additional time by a twice. Consequently, we can calculate a to the 49 using 7 matrix multiplications and not 48. Now that we have defined powers of linear operators, we can also define polynomials on linear operators. Let A be a linear operator. Then if we define P to be the polynomial such that P of A is equal to a squared plus 2a plus 6 times the identity operator, we now have a polynomial in A. Now, if the linear operators are real, that is, the linear operators map a real vector space onto or to a real vector to itself, then the coefficients of the polynomial must be from R. If, however, the linear operators are complex, that is, they are linear operators that map a complex vector space to itself, then the coefficients can come from the complex numbers. For example, given the polynomial p defined as p applied to a is a squared plus 2a minus 6 times the identity operator, and a is equal to the matrix 1, 2, 3, 4, we note that a squared is the product of a in itself, which is 7, 10, 15, 22. Twice a is equal to 2, 4, 6, 8. And negative 6 times the identity operator is the matrix negative 6, 0, 0, negative 6. Consequently, This polynomial evaluated at this operator is the sum of these three matrices, and summing up the individual entries, we get the matrix 3, 14, 21, 24. Now, notice here, for this polynomial, I was using a 2 by 2 matrix, but nothing in that polynomial says it must be a 2 by 2 matrix. Indeed, it could be a 10 by 10 matrix, a 20 by 20 matrix, or it could even be the differentiation operator. Following this topic, you now know how the identity operator applies to the vector space of all linear operators together with composition. You understand about the existence of compositional inverses. You know that composition is not commutative and not all operators have compositional inverses. You know how to find powers of matrices, and you understand that you can find polynomials on linear operators. Important point. From here on in this course, we will refer to the composition of linear operators as multiplication, and the compositional inverse will be referred to as the multiplicative inverse. Here are the references, acknowledgments, the colophon, and a disclaimer. Cheers!